Now, one other operation we need to talk about is traversal. So when we had our list data type, we wanted to visit all the nodes in the list and be able to print them out or perform some operation on them. And the whole point of having a set abstract data type is so that we can hold a collection of items and then possibly look at them and get them out. And so if we're going to hold items in an ordered set, we're going to need to be able to traverse them, which means we need to be able to do a tree traversal. We need to be able to walk through our tree and find all the data that we've previously put into our tree. Now, a tree traversal, the idea is that we would visit each node of the tree once and possibly perform some action. The action may be as simple as printing the contents, or it may be more sophisticated where you perform some operation on each node. Right? Unlike a list or an array traversal, which is fundamentally linear, right? With an array or a list, you can start at the beginning and just walk your way straight through it through memory, or by incrementing, moving to the next node in the list. Unlike those which are linear, tree traversals can happen in many different ways and actually many different orders, which could all be equally valid in some scenario. And so there are two general possibilities when you think about a tree traversal. Do you visit the node first, or do you visit the subtree first? And what I'm showing you here on the side is a tree made up of symbols and numbers. And it doesn't matter that this isn't a binary search tree. I just wanted a tree that would be easy for us to read and talk about. And so there are a few different ways we could traverse it, right? And it comes down to, do we visit the node first, or do we visit the subtree first? So let's say we visit the node first and the subtrees later. And what that means is I'm going to start at the root and I get to plus. And so I say, oh, I visited plus. And so over here, I write down plus to let me know I visited it. And I cannot visit it again once I visited once, okay? So plus has been visited. And then after plus, I go to its subtrees. So I'll just, as a matter of rule, we'll do the left side first. And so the next node we come to is star. And since we always do a node first before its subtree, that means the next thing we visit is star. So now we visited star. And then we do this process recursively. We go to star's left subtree. And so we visit 5. And so we say we visited 5. 5 doesn't have any subtrees, so there's nothing else to do. So that means we come back up and we say, okay, well, we last visited star. We last visited star's left subtree. Now we have to visit star's right subtree. So now we visit 6 next. But 6 doesn't have any subtrees, so we're done for everything at 6 after just visiting that node. So then we go back up to star and we realize, oh, we visited all of star's subtrees. So then we go back up again. And then we realize, oh, we did plus's left subtree, but we need to do its right subtree now. So then we would visit 7. And that would be the last node that we need to visit since C doesn't have any subtrees. Okay, so this would be one ordering, but you don't have to do it like that. You could visit the subtrees first. So what would happen if we visited the subtree first? Well, when we got to plus initially, we would say, no, wait, we'll visit this later. And then we would go to star, and we would decide to wait and visit it later. And then we get to 5. And so we visit 5 first, and we mark 5 visited. When we go up to star, we realize, oh, we have another subtree of star to visit. So we would visit 6. And so 6 would be the second node visited. Okay, then there's nothing else to do here. And so we realize, okay, now that we've done all of star's subtrees, we visit star. And so star would become next in the traversal ordering. Okay, after star, we'd go up to plus and realize there was more of that plus had another subtree. So we would visit that other subtree first. And so we'd visit 7. And now all of plus's subtrees are visited. So we would put the plus here. Okay, so from this tree, I came up with 2 different orderings. And there's even yet another ordering that we could consider as well, where we visit the nodes, where we visit a node in between the 2 subtrees, rather than either before or after. All of these different traversals have names and are useful in certain scenarios. And we tend to refer to these different traversals by certain common names to refer to the order in which we visit nodes with respect to subtrees. So a pre-order traversal is when we visit the node first, then the left subtree, then the right subtree. An in-order traversal is when we visit the left subtree, then the node, then the right subtree. And a post-order traversal is when we visit the left subtree, the right subtree, then the node. And these three traversals have different uses and different scenarios where they're very practical. And right now, we're really only going to focus on one of them, the in-order traversal. The in-order traversal on a BST matches the BST ordering. It will print out the nodes according to their order in the binary search tree. And that's what we want. We want to know the order of the set, so we want to know the BST order. So what in order, of course, means is that we visit the node in between the left subtree and the right subtree. And we do that because everything on the left is smaller than the node and everything on the right is bigger than the node. So if we go to the left subtree first, then the node, then the right subtree, that's proper numerical order. Now, to do a traversal like that in code is actually pretty simple using recursion. So this is not C++, this is just pseudocode, but the traversal, the recursive function here I'm calling tree traversal. It takes a node as an argument. And then the base case for the recursion is if the node is null, right? So if I get to a leaf node, I'll look at its two children and they'll both be null, and I'll call this function on them, and it won't do anything because they're null. It'll just stop recursion. So this is my base case. And then the first thing I do is I call tree traversal on the left node because those nodes are the smaller nodes and should come first. Then I visit the node I'm on, and then we call tree traversal on the subtree to the right to visit those. And maybe the only thing I would do here would be to print the node. So let's look at like how this code would execute over a tree. So we would always start at the root. So we'd call tree traversal on 9. And then 9 would have to call tree traversal on its left subtree first. So it would call tree traversal 5. And then 5 would have to call it on its left subtree first. So it would call tree traversal 3. And then 3 would do the same thing and call tree traversal 1. And at that moment, 1 doesn't have a left subtree. So we would just visit 1, and we're going to be done at that point and return. And when we return back to node 3, we would then visit 3 and then call tree traversal on 4. And likewise, 4 has no children, so it would be done. And it would return back to 3. And when it came back to 3, we had realized we had done all of the subtrees we needed to do, and it would just return back to 5. And then 5, we would visit 5 and then call tree traversal on 7, which would visit 7 because it doesn't have a left subtree. And then it would call tree traversal on 8, and we would visit 8. Okay, so visit 8 would happen. Since 8 doesn't have any children, it would quickly return back to 9. Now we finally made it to the middle of the tree, and there's nothing left to do on the left side, so we visit 9. And then we call tree traversal on 15. 15 has no left child, so we immediately visit 15 and then call tree traversal on 16. 16 would call tree traversal on 15 first, then we would visit 16, then we'd call tree traversal on 19. So if you look at where we visit nodes 1, 3, 4, 5, 7, 8, 9, 15, 16, 15, 15, 16, 19. Yeah, I forgot that I had a multi-set in here. 15 comes twice. Yeah, so we visit all, the order in which we actually visit the nodes is actually in BST order. If we wanted to do this in C++, it would look like this. Let's say we had that BT node object that we had before. We could pass the root of our tree into this tree traversal helper function. And then we would say if the node is null, we would just return. Otherwise, we call tree traversal helper on node left. And then after we do the left side, we just print out the value in this node. And then we would call tree traversal helper on the right side. And this would, in fact, enumerate all the nodes and print them out from smallest to largest. And now, amazingly, this basic traversal code, it works for all of the traversals that I told you about, pre-order, post-order, and in-order. All you have to do is change the relative order of traversal with respect to visiting the node. So if I wanted a pre-order traversal where I visit the node first and then the subtrees, then I would just move the visit node to above these two tree traversal calls. Whereas if I want a post-order traversal where I visit the node last, then I would just visit the node after these two recursive calls. So I can get 3 different traversal orders very naturally from this one recursive traversal algorithm. But what we really need for a binary search tree is the in-order traversal. So that's the one that matters the most for us for this particular data type. Okay, so tree traversals are important for visiting all of the nodes in a tree. Trees are not linear, hence many different orderings are possible. There are 3 kind of common traversals: in order, post order, and pre-order. Their implementations using recursion are very similar, varying really only in where you place the visit of the node. In order is most useful for binary search trees because it actually matches the value order of our set. And this in order would be a really useful way to, say, implement an iterator to walk over all the nodes in a binary search tree.